Hello everyone, welcome to JCE Connect. In previous class, we have discussed about loss of energy in pipes. That is, when a fluid is flowing through a pipe, the fluid experiences some resistance due to which some of the energy of the fluid is lost. This loss of energy is classified as two types. They are major energy loss and minor energy losses. So in previous class, we have also derived the equation for the major energy loss. That is this major energy loss, and this is due to mainly friction, and it is calculated by these two formulas, that is Darcy-Weisbach equation as well as Judge's formula. And in previous class, we have derived the equation for friction, that is a Darcy-Weisbach equation. Then also we have discussed about the minor energy losses. They are due to sudden expansion of pipe, sudden contraction, pipe in bend, there is bend in pipe, then pipe fittings, then an obstruction. So these all are minor energy losses. Okay, so the minor energy losses means whenever a fluid or the flow changes its direction or the cross section, that is the geometry, then these kind of losses will be occurring, and they are called as minor energy losses. So major energy loss, as I told, it is mainly because of friction, and the equation obtained as, so that is head loss due to friction, that is FL square by 2 GD, or it may be sometimes written as 4FL square by 2 GD. In this case, where F is the coefficient of friction, and if it is to be written in this format, FL square by 2 GD, where F represents the friction factor. So above mentioned equation is called the Darcy's Weisbach equation. It is valid for any fully developed steady incompressible pipe flow, whether the pipe is horizontal or on a hill. So this is the equation we have derived in previous class, that is Darcy's Weisbach equation, which is very useful for calculation of head loss due to friction. And today we are going to discuss about some of the minor losses. They are of loss of head due to sudden expansion. So here sudden expansion, in this case loss of head due to sudden expansion, and loss of head due to sudden contraction, that is this one sudden contraction, and this one sudden contraction, and this is sudden expansion. Then loss of head due to bend in the pipes, so this is the bend in the pipes, and loss of head due to pipe fittings, and also loss of head due to an obstruction in a pipe. So what equations can be used for calculation of these losses, we'll see in today's session. So let us derive first the equation, that is loss of head due to sudden enlargement. So this comes under minor loss, minor energy loss. So let us consider a liquid flowing through a pipe. In this pipe, consider pipe which has sudden enlargement as shown in this figure here. So the liquid is flowing from this section to this section, means from smaller section to larger section. So let us consider the two sections 1 and 2 before and after the enlargement. So this section is before the enlargement, and this section 2 is the after the enlargement. And let P1 be the pressure intensity at section 1 this P1 be the pressure intensity at section 1 and V1 be the velocity of flow at section 1 and A1 be the area pipe at section 1 at this section. And P2, V2 and A2 are the corresponding values at section 2. Okay. So this is the diagram. Okay. This is the diagram. Now, due to sudden change of diameter of the pipe from D1 to D2, the liquid flowing from the smaller pipe is not able to follow the abrupt change of the boundary. Thus, the flow separates from the boundary and turbulent eddies are formed as shown in this figure here. The loss of head or energy takes place due to the formation of these eddies. Means, so whenever the pipe or the flow changes from smaller section to the larger section, so suddenly it gets changes and the flow will not be following the boundary in this case. So in that case, the flow separates from the boundary. When it separates from the boundary, then the water starts whirling here. It starts whirling or rotating, and due to this whirling, the eddies will form. That is only here said. Thus, the flow separates from the boundary, and the turbulent eddies are formed. And these are the turbulent eddies. And the loss of head or the energy loss takes place due to the formation of these turbulence. So these are the eddies. Let P dash be the pressure intensity of the liquid eddies on the area A2 minus A1. This area is A1 and this area is A2. A2 minus A1, this is A2 minus A1. At this section, the pressure intensity will be P dash. So here the pressure intensity will be P dash, that is pressure intensity of the liquid eddies on the area A2 minus A1, and HE is the loss of head due to sudden enlargement. So HE represents the loss of head due to sudden enlargement. Then applying Bernoulli's equation at section 1.1 and 2.2, when we apply Bernoulli's equation at section 1.1 and 2.2, we get the energy at section 1 as this one, that is P1 by rho g plus V1 square by 2g plus Z1, that is energy at section 1.1, is equal to P2 by rho g plus V2 square by 2g plus Z2. This is the energy at section 2 plus the loss of head due to sudden enlargement. So in this pipe, Z1 is equal to Z2 because the pipe is horizontal. Then we get the equation as P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g plus HE. HE is the head loss due to sudden expansion. Then if we rearrange the terms, then we get head loss, that is due to expansion. P1 by rho g minus P2 by rho g is one term, and V1 square by 2g minus V2 square by is the another term. So let us call this equation number 1. So now consider the control volume of the liquid between the section 1.1 and 2.2. So whatever the area we have considered for the study purpose, let us call that area as a controlled volume area or control volume of the liquid between section 1.1 and 2.2. Then the force acting on the liquid in the control volume in the direction of flow is given by, that is Fx, that is a net force acting along the direction of flow, as P1A1, that is pressure force P1A1 in this section 1, plus P dash. P dash is the intensity of pressure due to the eddies acting over an area of A2 minus A1, that is also acting along the direction of flow, that is they are acting like this. Eddies will be acting like this, so they are along the direction of flow, that is P dash A2 minus A1 minus the pressure force at section 2, which is acting opposite to the direction of motion of fluid. So that is P2A2. P dash, that is P2A2, that is acting at section 2.2. Now, so but experimentally it is found that is eddies, whatever the pressure acting due to eddies, they are acting like this. This pressure is considered as a P dash. Experimentally, this intensity of pressure is found to be which is equal to P dash equal to P1 experiment. Now if you substitute in the above equation, that becomes a P1 A1 plus P1 into bracket A2 minus A1 minus P2 A2 is equal to P1 A2 minus P2 A2, which is equal to P1 A2 minus P2 A2. If we simplify P1 minus P2, that is if we take an A2 common, then P1 minus P2 into A2. Then applying the momentum equation, that is momentum of liquid per second at section 1.1 is equal to mass into velocity, that is rho A1 V1 is the mass into velocity V1, then it becomes rho A1 V1 square. Okay, this is the mass per second. Okay, mass per second. Then momentum of a liquid per second at section 2.2 will be rho A2 V2 is equal to V2, then rho A2 V2 square. Then change in momentum of per second equal to rho A2 V2 square minus rho A1 V1 square. But from the continuity equation, we have A1 V1 equal to A2 V2, or A1 equal to A2 by V2 by A2 V2 divided by V1. Then change of momentum per second will be rho A2 V2 V2, rho A2 V2 square minus rho into A2 V2 by V1. into V1 square. Then finally we get this equation. Then taking rho into A2 as a common, then V2 square minus V1 V2, we get this one. Then now the net force acting on the control volume, if it is control volume in the direction of flow, must be equal to the rate of change of momentum or the change of momentum per second. Hence the equation 2 and 3, P1 minus P2 into A2 is equal to rho A2 V2 square minus V1 into V2. So simplifying this one, we get V2 square minus V1 V2. Dividing by G on both the sides, we have P1 minus P2 divided by rho G, V2 square minus V1 into V2 divided by G, or P1 by rho G minus P2 by rho G is equal to V2 square minus V1 V2 divided by G. Substituting the value of P1 by rho G minus P2 by rho G in the equation number 1, we get this one, V2 square minus V1 V2 divided by G plus V1 square by 2G minus V2 square by 2G. This term we get. Then again simplifying, we get 2 V2 square minus 2 V1 V2 plus V1 square minus V2 square by 2G. Then 2 V2 square, and here is a V2 square, we will get a V2 square plus V1 square minus 2 V1 V2 by 2G. And this is nothing but A minus B whole square. So we get V1 minus V2 whole square by 2G. Okay, this only V1 minus V2 whole square by 2G. So V1 minus V2 whole square by 2G. The equation will be this one, V1 minus V2 whole square by 2G. So this is the equation, or this equation gives us loss due to sudden expansion, or energy loss due to sudden expansion. That is velocity at section 1 minus velocity at section 2 whole square by 2G. So this is the equation. Now the next is loss of head due to sudden contraction. So it's a reverse of sudden expansion. Initially the larger pipe, then the smaller pipe. Consider liquid flowing in a pipe which has a sudden contraction in area as shown in this figure, sudden contraction in this area. Consider the two sections again, one section 1 and 2 before and after the contraction. As the liquid flows from larger pipe to smaller pipe, means the liquid is flowing from this section to this section, means larger to smaller section. The area of flow goes on decreasing and becomes a minimum at section CC, means suddenly it is taking change over, means from the larger to smaller, then it will be bends like this, then it flows, then at this section the area will be minimum, and this is called the vena contracta. That is, it becomes a minimum at section CC. This section CC is called as vena contracta. After the section CC, a sudden enlargement of the area takes place. Means after this flow get contracted, when it becomes a minimum area at this CC, and after CC, a sudden enlargement of the area takes place. The loss of head due to sudden contraction is actually due to sudden enlargement from vena contracta to smaller pipe. Again, let AC be the area of flow at section CC. At this section CC, VC is the velocity of flow at section CC. Then A2 is the area of flow at section 22, and V2 is the velocity of flow at section 22, and HC is the loss of head due to sudden contraction. Then now HC is the actual loss of head due to sudden enlargement from section CC to section 22. Means here HC, if we want to calculate it, is actually loss of head due to sudden enlargement from section CC to section 22, and is given by the equation like a previous, that is loss due to sudden expansion, and it is here the actual losses are being taking place due to sudden enlargement, that is from CC to 22. Hence by utilizing the sudden enlargement equation, we can write equation here Vc minus V2 whole square by 2G, taking V2 square by 2G as a common, so it becomes Vc by V2 minus 1 whole square. So from continuity equation again we can write AC into Vc is equal to A2 V2, or Vc by V2 equal to A2 by AC, or 1 divided by AC by A2. So where ratio of contracted area divided by area at section 2, that is original area, gives us coefficient of contraction, that is 1 by Cc. Substituting the value of Vc by V2 in equation number 1, we get Hc equal to V2 square by 2G, that is when we take this as a common, 1 by Cc minus 1 whole square. So then we can write Hc is equal to K into V2 square by 2G, where K is called as loss constant for a sudden contraction, that is equal to 1 by cc minus 1 whole square. So if the value of cc is assumed to be equal to 0.62, then k value to be, it comes out to be 0.375 if we substitute in the above equation. Then the above equation Hc becomes, that is loss of head due to contraction becomes Hc equal to k v2 square by 2g, where value of k is 0.375, that is v2 square by 2g. If the value of cc is not given, then the head loss due to contraction is taken as approximately equal to 0.5 v2 square by 2g, or Hc is equal to 0.5 v2 square. So this is the equation we can use loss due to sudden contraction. Then here finally, this is the loss due to sudden expansion of pipe, that is from A1 to A2. When it is changing from A1 to A2, A1 is a smaller area and A2 is the larger area. When it is the flow is taking place from smaller area to larger area suddenly, then this is the equation can be used to calculate the energy losses due to sudden expansion, where V1 and V2 are the velocities of the liquid at area 1 and 2, where He is the loss at the entrance of the pipe. And this is the energy loss due to sudden contraction. This is the water flowing or the liquid flowing from the larger area to smaller area, that is from A1 to A2. Then the head loss due to sudden contraction, the equation can be used HL equal to KL into V2 square by 2G, where HC, that is point where KL is 0.5 V2 square by 2G. So where V2 velocity of liquid at section 2 in pipe and HC is the loss at entrance of the pipe. So these are the two equations, that is for the sudden expansion and for the sudden contraction. These are the equation to be used for the calculation of head loss due to expansion as well as for a contraction. Now here the loss of head at the entrance of the pipe. So this is also one more type of minor energy loss, that is loss of head at the entrance of the pipe. This loss of energy which occurs when a liquid enters a pipe which is connected to a large tank or a reservoir. This loss is similar to the loss of head due to sudden contraction. So this loss depends on the form of entrance. It depends on the form of entrance. For a sharp edge entrance, this loss is slightly more than a rounded or a bell-mouthed entrance. So when you compared with the sharp edge entrance with rounded, that is rounded or the bell-mouthed entrance, the sharp edged entrance will be having more losses. So in practice, the value of loss of head at the entrance or at the inlet of the pipe with a sharp cornered entrance is taken as 0.5 v square by 2g, where v is the velocity of the liquid in the pipe, and this loss is denoted by hi, that is loss at the inlet. So let us look here. So this is the tank, this one is the tank. So the water is entering from tank into the pipe like this, it is entering. So due to the entry, some losses will take place. It is as good as the loss due to sudden contraction only. So the equation to be used for this kind of loss as this one, that is Hi equal to 0.5 v square by 2g. So sharp edged entrance, this is the edge is sharp. So for the sharp edged entrance, the loss factor, that is KL, to be taken as 0.5, hence it is to be written Hi is equal to 0.5 v square by 2g, where v is the velocity of the liquid in the pipe and Hi is the loss at the exit of the pipe. Okay, so loss is, that is loss is at the entry of the pipe, not exit. It is for the entry of the pipe. This is entry of pipe, loss due to entry of pipe. So the loss at the exit of the pipe means this is the loss of head or energy due to the velocity of the liquid at outlet of the pipe, which is dissipated either in the form of a free jet like this, either in the form of free jet if outlet of the pipe is free, or it is lost in the tank or a reservoir. If the outlet of the pipe is connected to the tank or the reservoir, So this loss is equal to V square by 2G, where V is the velocity of the liquid at the outlet of the pipe. This loss is denoted as HO, that is outlet, which can be given as HO is equal to V square by 2G. Again, where V is the velocity of the liquid in the pipe and it is loss at the exit of the pipe, not the entrance, it is exit. Some mistake here. It is exit of the pipe. Means the water is exiting from this pipe into the tank, or it is into the atmosphere. So in that case there is a loss, and that loss is represented by V square by 2G. So this is the another type of minor loss, and many a times the liquid may get exit from pipe to the tank, or from the pipe to the atmosphere. In that case the loss to be represented as HO is equal to V square by 2G. Then the loss of head due to pipe bend in pipes. Many a times if we want to change the direction of flow, then the bends are being provided. Due to the bends provided in pipeline, due to bend provided in a pipeline, so there is a loss. Then when there is any bend in a pipe, the velocity of flow changes, due to which the separation of the flow from the boundary and also the formation of eddies takes place. Thus the energy is lost. And the loss of head in pipe due to bend is expressed as HB, which is represented as loss of head due to bend is equal to K into V square by 2G, where V is the velocity of flow and K is the coefficient of bend. Then the value of K depends on the angle of bend, and the value of this K depends on the angle of bend, the radius of curvature of the bend, and the diameter of the bend. Means at what angle the bend is being provided, it depends on that. This is the bend. Okay, sometimes the bend could be of any angle like this. The bend means it depends upon the angle of bend and the radius of curvature. How this one is the radius of curvature provided, radius of curvature, and the diameter of the pipe. Next is loss of head in various pipe fittings. So the loss of head in various pipe fittings such as valves, couplings, etc. if provided in pipelines, then the loss could be expressed as K into V square by 2G, where K is the coefficient of pipe fittings and V is the velocity of flow. This value of K to be calculated, and due to the various pipe fittings also the minor losses will take place, that is minor energy losses will take place. Okay. So these are some minor energy losses which generally come across in pipelines. Okay. I hope you understood these various types of minor energy losses. Out of these minor energy losses, that is the sudden contraction and sudden expansion losses in the pipes are of important for the examination point of view. In sudden enlargement equation, sometimes the equation can be asked for the derivation, and even sudden contraction also. And rest all losses, just you have to remember the equations whenever we solve a numericals. In that case we require these all equations, so you have to remember the equations. Thank you.